All right, so we just dealt with section 9.1, and that was all of our conic sections. And we will tie that back in a little bit to what we're doing today. Oh, well, not precisely today, but we'll tie that all in. So we dealt with conic sections in 9.1. 9.2 is about parametric equations. Now, for the most part, what we've done up till now is we've dealt with what we call rectangular equations. That is one equation that has a relationship between x and y. So if we have one equation with a relationship between x and y, like y equals 3x plus 2, then if you know the x, then you can find the y. Or if you know the y, you can find the x. Okay. Now what we're going to do is we're going to represent that same graph on the Cartesian coordinate system with two equations. We're going to have one equation for finding y and one equation for finding x. And we're going to introduce a new variable called t. Usually it's t. Can be other things as well, but t is probably the most common. And when we input a single value for t, we get an x and a y. So let me give you an example like this. In this case, if you input a t of 3, 1/3 times 3 gives you 1. So you get an x of 1 and a y of 5, right? 3 plus 2 is 5. Well, that's the exact same point you get here when you just input an x of 1, you get a y of 5. So we get the same point, but we have this extra variable. That's what I'm trying to get at. And we're going to get the same graph, but we're going to have this extra variable. And it turns out having that extra variable is nice. Because while one equation tells you position, that extra variable, or with that extra variable, you can also tell when a point is in a certain position. And that's why the variable is often called t. T is a lot of times a representation for time. So how does something travel? So while one equation tells you the position, that extra variable t tells you when the point is that position. And there's a lot of situations in which you want to know when something is located there. All right. So think of like the height of a bullet shot at a target, or think of something like a planet orbiting around a sun, or think about just traveling in a car. Your path of travel is important, but when you're at the precise locations, that's also important. And so we're going to get one equation to give us the x, one equation to give us the y. Oftentimes, notationally, we say x is equal to f of t and y is equal to g of t. We're going to see that when we get into the calculus of how to do calculus and derivatives and integration with parametrics. And then just so you know, the parametric equations together with the graph that they draw are called the plane curve. So the plane curve, the curve in the plane. All right. So for this section, what we're going to do is we're going to sketch the graph. We're going to change from rectangular to parametric. We're going to change from parametric to rectangular. Okay. So those are the things we're going to do in this section. In the next section, we'll do some calculus topics with parametrics. Right? But this section is just about understanding parametrics. So let's sketch x equals t squared minus 4 and y equals t over 2. Now there's a number of different ways to do the process of sketching a parametric. I'll show you a couple of different methods here in a minute. But the first method of sketching is finding a bunch of points. All right. So we often call this the table method or the find points method. Oh, let me take it one step back. Here I'm saying sketch x equals this, y equals this. You'll oftentimes see these notationally with a set bracket there so that you can see that they're a pair, right? Or even sometimes there'll be a set bracket around there so you can see that they work as a team, working as a pair. I typically don't do that in this class, but again, if you go into other books, sometimes you see that set bracket signifying that those are a pair. All right, so for finding points, what we're going to do is we're going to plug in different values for t. And that's going to give us our x value and our y value. So let's plug in something like -2. And then I'll plug in -1. I'll plug in 0. I'll plug in 1. I'll plug in 2. That's what we'll start with. If I plug in -2 to the x, I end up with a 0. -2 squared minus 4. If I plug in a -2 to the y, I get -1. If I plug in -1 into x, I get a -3. If I plug in -1 into my y equation, I get -1/2. I'm plugging in for t though, right? Maybe I misspoke, but plugging in 0, you get -4 for x. Plugging in 0, you get a 0 for y. And then let's do 1. Plugging in 1, you get a -3 for x. Plugging in 1, you get 1/2 for y. Plugging in 2, you get a 0 for x. Plugging in 2, you get a 1 for y. Let me go another. I'm going to plug in 4. If I plug in a 4, I get 12 for x. If I plug in a 4, I get a 2 for y. And now we have a bunch of points. We have a bunch of x, y pairs. 0, -1, -3, -1/2, -4, 0, -3, 1/2, 0, 1, and then 12, 2. And so hopefully we can kind of see what shape we're getting with the points. And the shape that I'm getting is a parabola pointed to the right. So here we have a parametric, or a set of parametric equations. We could plug in values for t, and then those values correspond to points on the graph. We see the pattern and we can, connect the dots. Now, that's a fairly long process for sketching a curve. It turns out that we can sketch the curve in other ways too, using technology. One of those ways is by going to something like Desmos. And graphing. So here's how we graph a set of parametric equations. What you do is you create a point, x comma y. And instead of the x, you put in the equation for t. And instead of y, you put in the equation for t. And then down here, it's going to say from what t starting value to what t ending value. Now, if you start and go from 0 to 1, you just get this part of the curve. So if we go, for instance, from a t value of -4 to a t value of +4, I get that parabola that I had graphed on the board. Notice that because I only went from -4 to +4, it kind of stops right here. If you wanted to go from, let's say, -8 to +8, then your graph's going to go further. But you'll have to denote where your starting and ending values for t are. So that's one option, is turn to Desmos and see how that works. Another option is to use your TI-84 calculator. See if I can. My projector got moved a bit, but there we go. So on the calculator, you can actually go through and graph with parametric equations. Now, if you're going to do this, the first thing you have to do is make sure the mode is correct. So hit the mode and then go down to parametric. So function, parametric, and then there's a polar. We'll deal with polar later too, but so now I want parametric, make sure that that's on. Now, when you hit your y equal button, here on the left-hand top, what you'll see is you'll be given pairs of equations. One that says x equals something and the other that says y equals something. And what we had was x equals t squared minus 4. Now the t that they want you to type in is the variable t. So this button here, t squared minus 4. Again, this variable key is what we're looking at. And then the y is going to be t divided by 2. I'm going to zoom this. So I'm going to zoom to the standard on my calculator screen, the standard view on my calculator screen. Oh, and what you see here is I got the top half of that parabola. Again, I'm only getting the top half because what my calculator's default setting does is it starts the t value at 0 and then goes up for a while. So if you want to change that, if you want to make sure t's can be negative, you just go to your window and change your t min and t max. The default is 0 to 2 pi. But if you change it from, let's say, -8 to +8, for instance, and then ask your calculator to graph, that's what you get. So you do get your parabola, again, as long as your t-value settings include the negatives. So now we just saw 3 ways to graph. One, by plotting a bunch of points. The second, by using Desmos with x comma y, and you just put in your equation for t in for x and your equation for x that involves the t in for the x spot, and your equation for y that involves the t in for the y spot. You create a point in Desmos with an arbitrary t, or you can graph using your TI-84. So that's a bunch of different ways to sketch. Oops. A curve. Trying to get to there we go. Parametric equation. I want you to do this. I want you to sketch this and go ahead and just use your calculator, or if you have access to a computer, use Desmos or your calculator, doesn't matter, to sketch this set of parametric equations. So if we have 8 cosine t and 8 sine t, 8 cosine t gives me my x value, 8 sine t gives me my what? Y value. It turns out you get a circle of radius 8 centered at the origin. Now, one thing about using your calculator, sometimes when you use your calculator, because the screen is not always a square, it's a little bit of a stretched out rectangle. Sometimes that circle won't look perfectly circular. So if you're using your TI-84 to do that, just note that your screen size kind of stretches things out. By the way, let's take a look at another one. 5 cosine t minus 1 and 7 sine t plus 3. So x equals 5 cosine t minus 1 and y equals 7 sine t plus 3. I think I'm just going to go ahead and graph that. 5 cosine t minus 1, 7 sine t, I think it was plus 3 if I'm remembering. Yep, plus 3. When you graph this, notice that you get a parabola, not parabola, excuse me, an ellipse, and the center of that ellipse is the point -1, 3. That's the center of the ellipse. Notice that that is corresponds to the -1 here in the x value and the plus 3 there in the y value. The other thing, the coefficient of the cosine is 5. And if you take your center of your ellipse and you move 5 units to the right, you end up at the right-hand vertex of the ellipse. If you take your center and you move 5 to the left, you end up at the left-hand vertex of the ellipse. And then similarly, if you move 7 up from the center and 7 down from the center, you end up at your upper and lower vertices for your ellipse. So the 5 is corresponding to essentially half of the length of the minor axis, what we used to call B in our equation with the ellipse. And the 7 is half the length of the major axis, which we used to call A in our equations of the ellipse. So we've seen 3 different conic sections in parametric form. We've seen the parabola, that was our example 1. We saw the circle, that was our example 2. Our example 3, we saw a parametric equation pair for an ellipse. And it turns out if we use secant and tangent instead of using sines and cosines, you can guess what's going to happen. If I do secant and tangent, notice that I'm getting an equation, or I should say a set of parametric equations, which produces a hyperbola. So we can sketch either by using points, like plotting points on a graph, or we can sketch by using technology. And we just saw in examples 1 through 4, all of our conic sections can be written in kind of interesting ways with parametrics. All of our conic sections, well, the parabola was written with just t's and t squareds, but the circle was written with trig functions, and the ellipse was written with trig functions, and the hyperbola was written with trig functions. So you can sketch those out if you like. Now, this takes us to converting from parametric form to rectangular form, or from rectangular form to parametric form. There's going to be basically 2 different substitution techniques that we're going to use to go back and forth. There's going to be what I like to deem, or what I like to call, direct substitution. And there's what I like to call indirect substitution. Direct substitution is exactly what it sounds like. I'm going to solve for one variable and I'm going to substitute it out. Indirect substitution, I'm still going to substitute out for variables, but I'm going to do so while taking advantage of some of the trig identities that we've seen. So indirect substitution is just substitution, but we're taking advantage of some trig identities, or technically they could be any identities that you want. But so let's take a look at this example. Here we want to go from parametric to rectangular. And by rectangular, we just mean using just the x and y's. And the parametric set of equations is x equals t squared minus 4, y equals t divided by 2. So what I'm going to do in that case is I'm going to pick an equation and solve it for t. The easier one for me to solve for t is y equals t over 2. And so I'm just going to multiply both sides by 2. And get 2y is equal to t. Now what I can do is I can substitute the expression for t in the other equation. In other words, I'm going to take x equals t squared minus 4, and I'm going to replace the t in this equation with 2y. Now be careful when you do that. Whenever you put something and you're substituting it in for t, make sure you put parentheses around it. So this is not just, this is the quantity 2y, quantity squared. It's not 2 times y squared. Does that make sense? And so my equation is essentially 4y squared minus 4. And that's it. That's the entire equation. You might ask, well, how far do we need to simplify or do we need to solve? When you convert to rectangular, you don't need to do a lot of simplification. All right. I think Moodle actually even recognizes this one. All right. With the 2y in parentheses squared. I like to, on the board, multiply that out, get 4y squared, but you don't have to. All right, let's do the same thing. We're starting with parametric, and we want to convert to a rectangular equation. We have x equals e to the 2t minus 4, and y equals 7t plus 3. Go ahead and use the same technique we did. That is, this is what I call direct substitution. Just solve for t in one of the equations. And then substitute in the other equation. All right, in this one, I would probably take y equals 7t plus 3 and solve that one for t. When you do that, you get y minus 3 equals 7t. Dividing by 7, y minus 3 over 7 is equal to t. And then substitute that into the other equation. So we have x equals e to the 2t and then minus 4. So in for this t, you put that entire expression. X equals e 2 times y minus 3 over 7. and then the whole thing minus 4. If you want to distribute your 2 in, that's fine. If not, it's not that big of a deal. I'm going to. But if you do distribute that in, you get e to the 2y minus 6 divided by 7 minus 4 is equal to x. So that's direct substitution, right? Both of those are just direct substitution. Now, to be able to do indirect substitution, we have to remember back to some trig identities. And in particular, the ones that are used a lot in this class, especially around conic sections, are the ones that we call the Pythagorean identities. Specifically, cosine squared plus sine squared equals 1. And the equivalent statement when we divide both sides of that equation by cosine squared. So let me go through. I'm just gonna so the Pythagorean trig identities. The first was that cosine squared plus sine squared is equal to 1. And then if you divide this by cosine squared, you get 1. If you divide sine squared by cosine squared, you get tangent squared. And if you do 1 divided by cosine squared, you get secant squared. Okay, remember those? Both of them. So let's take a look at, converting from parametric to rectangular using the indirect substitution. Here we have x equals 8 times cosine of t, y equals 8 times sine of t. So if we have sines and cosines, what we're going to do is we're going to use this trig identity. We are going to solve each for cosine and sine. So we're going to solve 1 for cosine of t and the other for sine of t. And then we're going to substitute that into our Pythagorean identity. So for instance, this one, we'd go x equals 8 times cosine of t. Dividing both sides by 8 gives me x over 8 is equal to cosine of t. Y equals 8 times sine of t. We divide both sides by 8 and say y over 8 is equal to sine of t. And now replace cosine of t and sine of t in the trig identity. Specifically, we're going to say cosine of t squared plus sine of t squared is equal to 1. I changed the arguments to match up with t's because that's what I had instead of, I didn't have thetas. By the way, sometimes with parametric, people will use theta because of these identities, but we had t. So cosine squared, that's cosine squared. So I replace that with x over 8. Replace cosine with x over 8. So I get x over 8 squared. Plus, now I can replace the sine with y over 8. Equals 1. Now, because of the way exponents work, I can square the numerator, square the denominator. I'm going to get x squared over 64 plus y squared over 64 is equal to 1. And then if I multiply both sides by 64, I get my standard equation for a circle of radius 8, centered at the origin. X squared plus y squared equals 64. So we use those Pythagorean identities and I use substitution, but I call it indirect substitution because you're substituting both the cosine and the sine. And you're using a trig identity. Now, let me state one other thing. This is the way I like to do this. Some people actually will manipulate the trig identity. And instead of substituting the cosine, they'll substitute 8 cosine. In other words, they will like multiply both sides by 64 and then substitute in 8 cosine. I think this is a little bit more straightforward, so, but it's not that much more straightforward than the other. So some people like to manipulate the trig identity first and then substitute in, and that way they don't have to solve all the way down here. Or they don't have to do y over 8 when they substitute in. Either way, you get the exact same answer. I want you to try this parametric to rectangular substitution on your own. X equals 5 secant of t minus 1. And y equals 7 tangent of t plus 3. All right. Same concept. We're gonna solve one for the trig. The trig expression secant t. We're gonna solve another for the trig expression tangent of t. So for x, I'd add 1 to both sides, and then I'd divide by 5. And I'd come up with x plus 1 over 5 is equal to the secant of t. For the y version, I'd subtract 3 from both sides, and then I'd divide by 7. And I'd get y minus 3 divided by 7 is equal to tangent of t. Now, in this case, some people will use this version of the trig identity. Other people will subtract tangent squared from both sides and use that version of the trig identity. So I think that's what I'll do. I'll subtract tangent squared from both sides. And if I do that, I get secant squared minus tangent squared is equal to 1. That's not something you absolutely have to do, but it's gonna make sense when you do your substitution. So now I'm gonna substitute x plus 1 over 5 in for my secant. And this is secant squared, so I'm gonna take x plus 1 over 5 quantity squared. Minus, when I substitute y minus 3 over 7 for tangent, I get y minus 3 over 7 quantity squared. I'm subtracting those two, and then they're becoming 1, equal to 1. What's going to happen? Well, I can rewrite this. Remember, squaring a fraction means I can square the numerator and then divide by the square of the denominator. And I end up with x plus 1 quantity squared divided by 25 minus y minus 3 quantity squared over 49 equaling 1. And we can all see that that is exactly our standard version of the hyperbola. So our standard version of the hyperbola. So that's why these weird equations with trig functions gave us like when we graph those, that's why when we sketch these, this looked like a hyperbola. And it's also why if you go through and do the same thing for example 3, that's why this one looks like an ellipse. And in example 2, that's why that looked like a circle. Think what's that have to do? But there it is. Now we can also convert to parametric using the same two tools that we just used to convert into rectangular. So we're going to go from rectangular to parametric now. Using the same tools. Okay. So we have y equals x squared minus 4x plus 7. Now, if we are using direct substitution, we don't need any trig identities or anything like that. We can simply make one of our variables equal to anything we want. All right. So since we're solved here for y, we can make the x anything we want, any expression in t that we want. So if you wanted to make x equals 7t plus 4, make x equals 7t plus 4. If you wanted to make your x equal to 3t minus 1, you make your x equal to 3t minus 1. Probably the easiest thing to do is to make x equal to t. If I set x equals t, then I can replace the x with the expression in the rectangular equation. In other words, I can replace the x everywhere I see it with the t. Right? And then my parametric set of equations has x equals t as the first equation and y equals t squared minus 4t plus 7 as the second equation. And that would be my parametric set of equations with direct substitution. Now, in this case, I substituted out the x value because we had already solved for y here. This also shows you that there's infinitely many different sets of parametric equations that you could get. You could have let our x be 2t, or 3t, or 4t, or 2t minus 1, or 2t minus 6, or 2t plus 4, right? You could have let your x be anything. So you get lots and lots and lots of options for parametric equation pairs of equations. right? But generally speaking, the easiest direct substitution is just letting x equals t. I want you to try using direct substitution this one. We have x. All right, so this one again, direct substitution. We already have this one solved for x. So instead of trying to force x to be equal to t, the easier way is to make y anything we want. Do you guys catch that? This one's already solved for x, so we're gonna make y anything we want. The easiest is usually y equals t, but if you wanted to do y equals t over 4, that'd be fine too. Or if you want to make y equals, whatever you want, you could make y equals whatever you want. All right? And then we're going to replace the y with the expression in the rectangular equation. So we're going to take the x equals 17e to the 4y and replace y with that expression. And again, I chose the easiest one, y equals t. So x equals 17 e to the 4 times t. So my parametric set has that equation for x equals 17 e to the 4 t. And for the equation for y, it's just y equals t. And again, there's lots and lots of choices for this. Infinitely many. I'd like to pick the easiest one when I can. So you can either make x anything you want or make y anything you want. That's especially nice when our equation has x equals an expression in y. Or like in the previous equation, we had y equals an expression in x. We can just use direct substitution. And if we had something where we could easily solve for x or easily solve for y, we do that and then do direct substitution like this. Now, the other type of substitution that we're going to deal with are going to be utilizing these equations. So it's going to be the indirect substitution. And it's going to look exactly like the reverse of what we just did. So here, is an ellipse. This is the standard version of an equation for an ellipse. X minus 4 squared over 25 plus y plus 2 squared over 4 is equal to 1. So we're going to use our Pythagorean identities. And because we have two things being squared adding up to be equal to 1, we're going to use this identity, right? And so our goal is going to get, or rewrite, maybe that's a better word, rewrite the equation to give me something squared plus something else squared equaling 1. That way I can just say, well, this got to be cosine, this got to be sine, and then we're good to go. So how we do that, since I want a single thing to be squared, I'm going to rewrite this into x minus 4 divided by 5, all squared. Quantity squared. And on this other one, I'm going to have y plus 2 divided by 2, quantity squared equaling 1. And then, since we now have the form cosine squared, I'll use t, plus sine squared of t equals 1. You can also use theta there if you prefer to use the variable theta. Moodle will tell you which variable to use, t or theta or whatever. But, so since we have that form, we can say that x minus 4 over 5 can be set to be cosine of t, and y plus 2 over 2 can be set to be sine of t. We're going to take this one, we're going to multiply both sides by 5. That's going to give us an x minus 4 is equal to 5 times the cosine of t. Over here, we're going to multiply both sides by 2. We're going to get y plus 2 is equal to 2 times the sine of t. In the left-hand equation, the equation for x, I just have to add 4 to both sides. I'm not writing down all the steps because they're pretty straightforward. In the left-hand equation, I'm going to subtract 2 from both sides. And so the parametric set of equations, the one for x is equal to 5 times the cosine of t plus 4. and the other is y equals 2 times the sine of t minus 2. So those would be the parametric equations representing this standard form of an ellipse. Try example 12 on your own. All right. So the Pythagorean identity that we want to use here, because we have something squared minus something else squared, is this one. And again, I like using this version of it or this version where the one's on the right side, but it doesn't matter. So we're going to use the secant squared minus tangent squared identity. And before we get to replace that or do my substitutions, I need to write this whole fraction as being something squared. So I get y plus 5 over 7 squared minus x minus 8 divided by 6 squared equals 1. So make sure you convert those things to something squared minus something else squared. Now I have that form that I want, the secant squared minus tangent squared form. Be very careful here that you get the right one associated with the right expression. The minus, we're subtracting 8 minus, x minus 8 over 6 quantity squared. So that has to be the tangent part. And I'm going to say tangent of t. Again, if you want to say tangent of theta and use theta as your variable, that's fine too. And then the y plus 5 over 7 has to be the secant part. Just as a side note, in this identity, the cosine and the sine are kind of interchangeable, right? They play the same role. So in our previous problem, technically we could have associated with the sine with the x value and the cosine with the y value in our previous problem. However, traditionally, people associate the cosine with the x value and the sine with the y value because of the relationship with the unit circle. So that's the traditional way of doing it. And this, you cannot interchange secant and tangent. Tangent squared minus secant squared is not the same thing as secant squared minus tangent squared. So this one you have to be very careful about which ones. Now, to solve for x, we're going to multiply both sides by 6 and then add 8. I'm just going to do that in my head here. When you multiply both sides by 6, you get 6 times tangent of t, and then add 8. 6 tangent t plus 8 is equal to x. And then when I solve this one for y, I'm going to have to multiply both sides by 7 and then subtract 5. When you do that, you get y is equal to 7 times secant of t minus 5. And there's my set of parametric equations. And those parametric equations give me the same graph as this rectangular equation. So I get a hyperbola in either case. So that's the indirect substitution. And if I ask you to do indirect substitution in this class, it's going to be using these trig identities. Okay? One of those trig identities. There are other trig identities that you could use with indirect substitution. There's other algebraic identities you could use with indirect substitution as well. But these are the ones that are important and connect back to conic sections. So those are the ones that we're going to deal with. But I don't want you to think that's the only type of substitution you can do with parametrics. Like there's all kinds of different identities, both algebraic and trig identities. You can do that. Okay. Now we just got done going through converting from rectangular to parametric. And you can see now that if you're looking for ellipses in parametric form, you can do x equals a times cosine of t plus h, y equals b times sine of t plus k, and that gives you an ellipse with center hk. horizontal axis length 2A and vertical axis length 2B. Now, if A is bigger than B, then the horizontal axis is the major axis. If your vertical axis is actually longer than your horizontal axis, you might want to switch the roles of A and B. And swap where A and B's are, but you guys get the point, right? And then the hyperbola equations. Well, we saw x is equal to something times tangent of t plus a number, and y is equal to something times the secant of t plus a number. That was a hyperbola. Pointed up and down. If you want a hyperbola pointed left and right, you have to put your secant with your x and your tangent with your y. Those are going to give you hyperbolas with asymptotes of slope plus or minus b over a. So your tangent, your secant give you the hyperbola equations. That's all we're saying there. All right. Tangent, secant give you hyperbola, and putting tangent with the x and secant with the y gives you a hyperbola pointed up and down. Putting the secant with the x and the tangent with the y gives you a hyperbola pointed left and right. By the way, there's some really interesting parametric curves that you can get. You don't have to memorize any of these. I'm just showing you kind of some interesting graphs that you can get. You can get an asteroid if you take x equals cosine to the third power and y equals sine to the third power. You can get a hyptrocoid. That's kind of a messy formula, but it looks like a star. One kind of well-known parametric curve is a rose curve. A rose curve just has a bunch of petals. We'll see this in polar form too, but in parametric form, it's cosine t sine of 4t. And if you change that 4 into another number, like 5 or 6, then that changes the number of petals you get. All right, I'll show you that in just a moment. And then there's like this ellipticoid. That's an interesting thing too. Now, I'm not concerned. You should not memorize these. These are not something you have to memorize the equations for. I'm just saying we can get lots of really interesting shapes using parametric. And what you'll notice is that these interesting shapes are actually not functions where you can solve for y. You can't have y is equal to a function of x. And that's the same with parametric versions of conic sections too. A lot of conic sections, we can't write as y equals a function of x because they fail the vertical line test. And you can see a lot of these also fail the vertical line test. And the reason I point that out is because a lot of the calculus that we've done so far has been on stuff where I can write y equals a function of x. And then I take the derivative, or I integrate on something that looks like y is a function of x. Here, these won't be able to be written that way, these graphs, but I can still do things like find the tangent line or find the slope of the tangent line. I still should be able to integrate things of that nature. Let me just for a moment explore that sine curve. Did I say sine curve? I'm sorry, rose curve. Let's do the rose curve. It said sine because they use sine in there. There we go. Now I'm zoomed out, but if you zoom in, so when I had sine of 4t, I got 8 petals. If you change that 4 to a 6, and this other 4 to a 6, what's going to happen is you're going to get 12 petals. All right. And if you change the 6 to an 8 and the other 6 to an 8, it turns out you get 16 petals. So 4, 6, 8, all even numbers in there, you get double the numbers of petals. Interestingly enough, if you put in an odd number like 5, you get exactly 5 petals. Or if you put in a 7, you get exactly 7 petals. So the odd numbers, when you put them in there, give you the exact number of petals. Where if you put in the even numbers, you get double that number of petals. And by the way, they use sine on both of these. If you had, oh shoot, I'm going to copy paste. If you change the sine to a cosine, oh, I see why. You still get a rose curve. It's just slightly rotated. It's rotated, and it's rotated. So one of the main petals is on the x-axis when you do cosine. And one of the main petals will be on the y-axis if you do sine. Does that make sense? Will be right along the y-axis. So that's the difference between using sines and cosines. I know the book didn't have that, but that's just kind of an interesting thing. So these rose curves are also kind of an interesting picture that you can get. And weirdly enough, change the 7 to 3 on both, you'll get 3 petals. Change it to, I don't know, 15 on both, you'll get 15 petals. And one of the petals, since we're dealing with cosines, one of them will be right along the x-axis. You always get one right along the x-axis there. Okay. And if you do the same thing, mess around with sine, no matter what you change this to, if it's odd, you'll get one pedal along the y-axis. Sometimes it'll be pointing up, sometimes it'll be pointing down, but that's the idea. Okay. So kind of interesting things we can get with parametrics. And because we can get these interesting graphs, and because sometimes the equations are nicer to deal with in parametric form than they are in rectangular form, sometimes it's going to be nicer to deal with some calculus topics with the parametric rather than with the rectangular. And so we're going to see how to do some basic calculus things with parametric equations in 9.3. Now let me do something real quick. All right, so here's what I'll do. Instead of starting this today, I think what I'll do is I'll make this a clean break where 9.2 is done today, and we'll start in with the calculus topics and how to do some of the basic calculus concepts with parametric stuff on Thursday. All right, so we'll do that instead of trying to start and begin 9.3 today. All right, I'll see you on Thursday.